Welcome! In this session, we'll explore the problem number 977, squares of a sorted array. This problem challenges us to transform an input array by squaring each number and then returning the results in sorted order. It's a classic problem that tests our algorithmic thinking and optimization skills. Let's dive in and uncover the best approaches to solve it. In this problem, we're given an integer array nums that is sorted in non-decreasing order. The task is to return a new array containing the squares of each number in nums, also sorted in non-decreasing order. Let's take a closer look at the input and output formats. The input is an integer array nums of size n that is already sorted in non-decreasing order. For the output, we need to produce an array where each number from nums has been squared, and these squared values are sorted in non-decreasing order. To make this more concrete, let's consider an example. If nums is -4, -1, 0, 3, 10, squaring each number gives us 16, 1, 0, 9, 100, and sorting these values results in 0, 1, 9, 16, 100, which is the final output. Now, let's go through another example to better understand the process. If nums is -7, -3, 2, 3, 11, the first step is to square each number. This gives us 49, 9, 4, 9, 121. Notice that the squared values are not in order yet, so the next step is to sort them in non-decreasing order. After sorting, the result is 4, 9, 9, 49, 121. Let's look at one more example. If nums is -5, -3, -2, -1, squaring the numbers results in 25, 9, 4, 1. Sorting these values gives 1, 4, 9, 25. This highlights that while the input is sorted, the squaring process can disrupt this order, so sorting the squared values is a necessary step. Now, let's take a look at the constraints and some edge cases that can arise in this problem. The constraints specify that the length of nums will be at least 1 and at most 10,000, and each number in nums will fall between -10,000 and 10,000. Importantly, the input array is guaranteed to be sorted in non-decreasing order. For edge cases, consider arrays with all negative numbers, such as -5, -4, -2. Squaring makes all elements positive, and sorting ensures the output is in non-decreasing order. For arrays with all positive numbers, such as 1, 2, 3, the order remains unchanged because squaring positive numbers doesn't disrupt their order. Mixed arrays, like -2, -1, 0, 1, 2, require careful handling because squaring negative numbers makes them positive, and a resort is needed to produce the correct result. Finally, let's discuss a few more edge cases and an efficient approach to solve the problem. Arrays with a single element, such as 0 or -3, are straightforward since squaring the single number directly gives the output. Arrays with zeros, like -3, -2, 0, 2, 3, will include the 0 in the output, and it naturally appears at the beginning after sorting. To solve the problem efficiently, we can use a two-pointer approach. Place one pointer at the beginning of the array and another at the end. Compare the absolute values of the numbers at these pointers. The larger absolute value will produce the largest square, so we place that square at the end of a result array and move the corresponding pointer inward. Repeat this process until all elements are processed. Since we're filling the result array in reverse order, no additional sorting is required. This approach ensures an efficient solution with minimal extra computation. To solve the problem of finding the squares of a sorted array, one straightforward approach is the brute force method. Here's how it works. First, we calculate the square of each number in the input array. For instance, if the input is -4, -1, 0, 3, 10, we square each element to get 16, 1, 0, 9, 100. Then, we sort this resulting array to produce the final output in non-decreasing order, which would be 0, 1, 9, 16, 100. While this approach is easy to implement, it does not take advantage of the fact that the input array is already sorted. This inefficiency arises because we use a sorting step, which dominates the overall time complexity, making it an asterisk log n. For an array of size n. Additionally, we need extra space to store the squared values, resulting in a space complexity of n. So, while simple, this approach is not optimal. The brute force method, as we just discussed, has a time complexity of n plus n asterisk log n, which simplifies to n asterisk log n due to the sorting step. Additionally, its space complexity is O(n), because we allocate space for the squared values. While the brute force approach is straightforward and easy to code, it is suboptimal because it fails to exploit the sorted nature of the input array. This leads us to consider a more efficient solution, the optimized two-pointer approach. By leveraging the fact that the input array is already sorted, we can identify that the largest absolute values, and therefore the largest squares, will always come from either the leftmost or rightmost ends of the array. This insight allows us to use a two-pointer technique to directly construct the output array in sorted order without requiring an additional sorting step. This makes the process significantly faster and more efficient. The two-pointer approach works as follows. First, we initialize two pointers, one at the start of the array, called left, and another at the end of the array, called right. We also create an output array initialized with zeros, which has the same size as the input array. Next, we iterate backward through the output array, filling it from the largest square to the smallest. At each step, we compare the squares of the elements at the left and right pointers. The larger square is placed at the current position in the output array. If the square from the left pointer is larger, we move the left pointer one step to the right. Otherwise, we move the right pointer one step to the left. This process continues until all elements from the input array are processed. Since we only iterate through the array once, the time complexity of this approach is O(n). The space complexity remains O(n) due to the output array. While the implementation is slightly more complex than the brute force method, this strategy is optimal because it eliminates the need for sorting and fully utilizes the sorted property of the input array. The optimized two-pointer approach is the preferred solution for this problem, and here's why. First, it has a linear time complexity of O(n), which is significantly more efficient than the O(n*log(n) complexity of the brute force method. Second, it avoids the unnecessary overhead of sorting by directly constructing the output array in sorted order. Most importantly, this approach takes full advantage of the fact that the input array is already sorted. The key insight that makes this method efficient is recognizing that the largest absolute values, and therefore the largest squares, are located at the boundaries of the array. By comparing these values and filling the output array from largest to smallest, we eliminate the need for additional processing. When comparing the two approaches, the brute force method is simpler to implement but computationally expensive, while the two-pointer method is both efficient and memory conscious. For these reasons, the two-pointer approach is the superior choice for solving this problem. The problem we're tackling is to compute the squares of a sorted integer array and return those squares in non-decreasing order. The array can include both negative and positive numbers, which makes it interesting because squaring negative numbers can result in larger values than squaring positives. For example, given the input array nums equals -4, -1, 0, 3, 10, squaring each number results in 16, 1, 0, 9, 100. Sorting these squares gives the output 0, 1, 9, 16, 100. The challenge here is to achieve this efficiently, without needing to first compute all the squares and then sort them, which would be less optimal. To solve this problem efficiently, we use the two-pointer approach, which is ideal for sorted arrays. This method leverages the fact that our input is already sorted in non-decreasing order. First, we initialize two pointers. The left pointer starts at the beginning of the array, while the right pointer starts at the end. We also create an empty result array of the same size as the input, initialized with zeros. This result array will store the squared values in sorted order. To determine where the next largest square should go, we use a right pointer, which initially points to the last index of the result array. By filling the array from the back, we can avoid additional sorting steps and directly place the largest squared values in their correct positions. The main part of the algorithm involves iterating while the left pointer does not surpass the right pointer. At each step, we compare the absolute values of the elements pointed to by left and right. If the absolute value at left is greater, we square that value, place it in the result array at the current right position, and move the left pointer one step forward. Otherwise, we square the value at right, place it in the result array at the right position, and move the right pointer one step backward. After placing the square, we decrement the right pointer to move to the next position in the result array. Once the pointers cross, all elements have been processed, and the result array contains the squares in sorted order, ready to be returned. This approach is efficient for several reasons. First, the two-pointer technique is well suited for this problem because the input array is sorted, and negative numbers can produce larger squares than positive numbers. By comparing the absolute values from both ends of the array, we can efficiently find the largest square at each step without processing the entire array first. Second, filling the result array backwards ensures that we directly place the largest squares in their correct positions, eliminating the need for additional sorting or shifting. In terms of complexity, the algorithm processes each element exactly once, making the time complexity O(n). The space complexity is O(n) due to the result array, but no additional data structures are required, so the memory usage is minimal. The data structures used in this algorithm are simple yet effective. The result array is the main storage for the squared values in sorted order, requiring O(n) space. The pointers left, right, and right are basic integer variables that track positions in the input and result arrays and operate in constant space. Let's consider an example to see how these components work together. For the input nums equals -4, -1, 0, 3, 10, we start by initializing left equals 0, right equals 4, right equals 4, and result equals 0, 0, 0, 0, 0. In the first iteration, we compare the absolute values of nums left and nums right, which are 4 and 10. Since 10 has the greater absolute value, we square it, write 100 to result 4, decrement right to 3, and move right to 3. Now, the result array looks like 0, 0, 0, 0, 100. In the second iteration, we compare the absolute values again, this time between nums left 4 and nums right 3. Since 4 has the greater absolute value, we square it, write 16 to result 3, increment left to 1, and move right to 2. The result array now becomes 0, 0, 0, 16, 100. This process continues, comparing, squaring, and writing values, until the left pointer surpasses the right pointer. At this point, all elements have been processed, and the result array contains the sorted squares. For the input nums equals -4, -1, 0, 3, 10, the final result is 0, 1, 9, 16, 100. This demonstrates how the two-pointer approach efficiently constructs the sorted squares without requiring additional sorting steps. Finally, let's consider some edge cases to ensure the algorithm handles all scenarios. If the input contains only positive numbers, such as 1, 2, 3, the largest numbers are already at the end, so the algorithm works as expected. For arrays of only negative numbers, like -3, -2, -1, the absolute values are sorted, so the two-pointer approach still applies. A single-element array, such as 5 or -5, is naturally handled because the left and right pointers both start at the same position. Arrays with zeros, like 0, 0, 0, also work correctly since squaring zeros results in zeros, and the output remains 0, 0, 0. These edge cases confirm the robustness of the algorithm across a variety of inputs. The implementation uses a two-pointer approach to solve the problem efficiently. Since the input array is sorted in non-decreasing order, the largest absolute values will be at either end of the array. The goal is to square the elements and place them in the result array in sorted order. The function begins by initializing two pointers, left and right, to point to the start and end of the array. It also creates an empty result array of the same length as the input array to store the squared values. A reverse loop is used to fill the result array from the largest squared value to the smallest. At each iteration, the absolute values of the elements at the left and right pointers are compared. The larger of the two is squared and placed at the current position in the result array. If the left value is used, the left pointer is increment, otherwise, the right pointer is decrement. This process continues until all elements have been processed. Since the loop runs once per element, the time complexity is O(n), where n is the length of the input array. The space complexity is O(n), due to the use of the result array. This approach is both efficient and easy to understand, making it well suited for solving the problem within the constraints provided by LeetCode. This is the Java implementation of LeetCode problem number 977, squares of a sorted array. The logic mirrors the Python version, using a two-pointer approach to efficiently fill the result array from the largest square to the smallest. Key differences include explicit type declarations and array handling in Java. The math.abs method is used to compare absolute values, and the result array is populated in reverse to ensure the sorted order. To solve this problem, we start with the input array nums equals -4, -1, 0, 3, 10. Our goal is to return a new array where the squares of the elements are sorted in non-decreasing order. To do this efficiently, we use a two-pointer approach. We initialize left to point to the first element at index 0 and right to the last element at index 4. We also create a result array of the same length, initialized to zeros, to store the squared values in sorted order. In the first iteration, we compare the absolute values of the elements at the left and right pointers. Here, abs, nums, left, is 4, and abs, nums, right, is 10. Since 10 is greater, we square nums, right, to get 100 and place it at the last position of the result array. We then decrement the right pointer to move inward. After this step, the result array is updated to 0, 0, 0, 0, 100. In the second iteration, abs, nums, left, remains 4, and abs, nums, right, is now 3. Since 4 is greater, we square nums, left, to get 16 and place it in the next available position from the right in the result array. We then increment the left pointer and update the result array to 0, 0, 0, 16, 100. In the third iteration, the values at the left and right pointers are compared again. Here, abs, nums, left, is 1, and abs, nums, right, is 3. Since 3 is greater, we square nums, right, to get 9 and place it in the next available position in the result array. We then decrement the right pointer, and the result array becomes 0, 0, 9, 16, 100. In the following iteration, abs, nums, left, is 1, and abs, nums, right, is 0. Since 1 is greater, we square nums, left, to get 1 and place it in the result array. This time, we increment the left pointer, and the result array updates to 0, 1, 9, 16, 100. Finally, in the last iteration, there is only one element left at the left pointer, which is 0. We square it to get 0 and place it in the first position of the result array. With that, the final result is 0, 1, 9, 16, 100, which is the output for this example. Now, let's look at another example with the input array nums equals -7, -3, 2, 3, 11. As before, we initialize left at 0, right at 4, and the result array is 0, 0, 0, 0, 0. In the first iteration, we compare abs, nums, left, which is 7, and abs, nums, right, which is 11. Since 11 is greater, we square nums, right, to get 121 and place it at the last position of the result array. We then decrement the right pointer, and the result array becomes 0, 0, 0, 0, 121. In the second iteration, abs, nums, left, remains 7, and abs, nums, right, is now 3. This time, 7 is greater, so we square nums, left, to get 49 and place it in the next available position in the result array. We increment the left pointer, and the result array updates to 0, 0, 0, 49, 121. In the third iteration, the absolute values at the left and right pointers are both 3. When the values are equal, we can choose either side to square, so we square nums, right, to get 9 and place it in the result array. Afterward, we decrement the right pointer, and the result array updates to 0, 0, 9, 49, 121. Next, we compare abs, nums, left, which is 3, and abs, nums, right, which is 2. Since 3 is greater, we square nums, left, to get 9 and place it in the next position in the result array. We then increment the left pointer, and the result array becomes 0, 9, 9, 49, 121. Finally, with only one element left at the right pointer, we square nums, right, to get 4 and place it in the first position of the result array. The final sorted array of squares is 4, 9, 9, 49, 121. For the third example, we start with the input nums equals -5, -4, -3, -2, -1. The left pointer is at 0, the right pointer is at 4, and the result array is initialized as 0, 0, 0, 0, 0. In the first iteration, we compare abs, nums, left, which is 5, and abs, nums, right, which is 1. Since 5 is greater, we square nums, left, to get 25 and place it at the last position of the result array. We then increment the left pointer, and the result array updates to 0, 0, 0, 0, 25. In the second iteration, abs, nums, left, is 4, and abs, nums, right, is still 1. Again, 4 is greater, so we square nums, left, to get 16 and place it in the next position of the result array. The left pointer is incremented once more, and the result array becomes 0, 0, 0, 16, 25. We then repeat similar steps for the remaining iterations. For each step, we compare the absolute values of the elements at the left and right pointers, square the larger value, and place it in the correct position in the result array. By the time all iterations are complete, the result array becomes 1, 4, 9, 16, 25. This is the final sorted array of squares, and it's returned as the output for this example. To analyze the time complexity of the algorithm, we start by considering how the input array nums is processed. The two-pointer approach ensures that the array is traversed only once. First, initializing the two pointers, left and right, along with the result array, only requires constant time, or O1. Then, during the main loop, we iterate through the array exactly once with a for loop. In each iteration, one of the two pointers moves inward by one step, and we perform a constant number of operations, such as comparisons, squaring a value, and assigning it to the result array. Since the loop runs for each of the n elements in the array, the total work done inside the loop scales linearly with the size of the input. Importantly, there are no nested loops or recursive calls that could add extra computational layers. Therefore, the overall time complexity of this algorithm is O(n). Now, turning to space complexity, the algorithm is efficient in its use of memory. The input array nums is read-only, meaning it doesn't require any additional space. However, to store the results, we create a new result array, which is of the same size as the input array. If the input array has n elements, the space required for this array is O(n). Beyond that, the algorithm uses only a few integer variables, such as left, right, and an index variable, all of which require constant space, or O1. Since no additional data structures like stacks or hash maps are utilized, the total space complexity is dominated by the result array, making it O(n). Let's compare this optimized approach to a naive solution. A brute force method might involve squaring all the elements in the input array first, which takes O(n), and then sorting the squared values. The sorting step, using a typical sorting algorithm, would take O(n*log n). This results in a total time complexity of O(n plus n*log n, which simplifies to O(n*log n). The space complexity for this naive method would still be O(n), due to the array holding the squared values. In contrast, our optimized two-pointer approach takes advantage of the fact that the input array is already sorted in non-decreasing order. By filling the result array in reverse order using two pointers, it eliminates the need for an explicit sort, reducing the time complexity to O(n). This is a significant improvement, especially for larger inputs. Additionally, the time complexity remains O(n) for all cases best, average, and worst, since the algorithm always processes the entire array in a single pass, regardless of the input distribution. Finally, to formally prove the time complexity of O(n), consider that the for loop executes exactly n iterations, where each iteration involves operations that take constant time, or O1. Multiplying the n iterations by the constant cost per iteration gives a total of n*O1, which simplifies to O(n). Furthermore, there are no other significant operations outside the loop that could contribute additional time complexity. For space, the only extra memory used is the result array, which matches the size of the input array, resulting in O(n) space complexity. The auxiliary variables require only O1 space, so they don't affect the overall complexity. This confirms that the algorithm operates with a time complexity of O(n) and a space complexity of O(n). When solving this problem, there are some common mistakes to watch out for. First, forgetting to handle negative numbers can cause issues because squaring negative numbers results in positive values, which may disrupt the sorted output if not handled correctly. To fix this, make sure to sort the array of squared numbers after computing the squares. Another mistake is relying on inefficient sorting methods for large arrays. Using nums.sort has a time complexity of O(n log n, which is less optimal than the O(n) two-pointer approach. The two-pointer method avoids explicitly sorting and instead merges the squared values in sorted order directly. Additionally, some assume that the input is already sorted in absolute values, which isn't always true. Even if the array is sorted in increasing order, the square of negative numbers can change the sequence. Always analyze the problem constraints carefully. Finally, modifying the input array directly can lead to unexpected behavior, especially in coding interviews. It's better to create a new array for squared values to preserve the original input and maintain immutability, which is often preferred in these scenarios. Now, let's consider other potential pitfalls and insights. Overlooking edge cases like an empty array, arrays with all negative numbers, or arrays filled with zeros can lead to runtime errors or incorrect outputs. The solution should be tested against a variety of edge cases to ensure robustness. From an interview perspective, this problem often tests your ability to optimize a brute force solution into something more efficient. While explaining your approach, start with the brute force method to show your thought process, but quickly transition to the optimal two-pointer solution. It's also important to discuss time complexities. Highlight that the two-pointer approach achieves O(n) complexity compared to the O(n) log n complexity of sorting-based methods. Additionally, focus on writing clean, modular code with clear logical steps and comments. Interviewers appreciate clarity in your explanation and implementation. Be prepared to explicitly address edge cases, such as handling negative numbers, zeros, and arrays with very small sizes, including those with only 1 or 0 elements. This problem is closely related to several others that involve sorted arrays and the two-pointer strategy. For example, in LeetCode 167, 2sum2, you use a similar two-pointer technique to find pairs of numbers that sum to a target value in a sorted array. LeetCode 15, 3sum, extends this idea by searching for triplets that meet specific conditions, requiring careful pointer management. Similarly, LeetCode 16, 3sum closest, builds upon the two-pointer method but introduces additional constraints to find the closest sum to a target. Finally, LeetCode 88, merge sorted array, involves merging two sorted arrays into one while maintaining their order, which parallels the merging logic used in the two-pointer approach for this problem. Exploring these related problems can deepen your understanding of how the two-pointer strategy can be adapted to solve a variety of challenges. There are also alternative approaches to solving this problem, each with its own trade-offs. The brute force approach involves squaring each number and then sorting the resulting array. While this method is simple to implement, it has a time complexity of O(n) log n, making it inefficient for large inputs. A more efficient alternative is the two-pointer approach. By placing pointers at the start and end of the array, you can merge the squared values in sorted order without explicitly sorting. This method achieves O(n) complexity but requires careful pointer management to ensure correctness. Another option is the heap-based approach, where you push squared values into a min heap and extract them in sorted order. While this method is cleaner and avoids pointer management, it still has a time complexity of O(n) log n, making it less efficient than the two-pointer approach. Understanding these trade-offs can help you choose the best solution based on the problem constraints and requirements. Thank you for joining this session. We reviewed the problem, explored solutions, and highlighted key insights to optimize performance. Remember, mastering these techniques is essential for tackling similar array manipulation problems efficiently. Stay motivated, keep practicing, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!